Hi, we're doing a distribution. We're doing a video on distributions. I haven't done these in a while, not the distributions, but the videos. So you may need to be a little bit patient. Plus, the writing is on a new type of tablet, so it might be messy till I get used to it. So in this section, this would go with Dr. Reyes's Module 3, Video 2, we're looking at a distribution, and a distribution is really just a representation of the population or a sample, like through a table or through a graphic, kind of the shape, the center, how spread out it is. So a distribution, it really helps to characterize a distribution with three different aspects of it. So the location really describes where the values are concentrated. The spread really talks about the degree to which the values are concentrated. So often we look at the spread about the mean, how much variance, how much spread, how much distance you have from the center. Is everybody, all your x's really clinging close to your mean? Are they well spread out? The shape is, I would just say the shape is the shape. In his notes, he says that the shape describes the pattern of the values. Let me give you an example. Here's one with a shape. So I'm going to draw the shape being a bell curve. So that is one type of shape of a distribution. I would say this guy is centered, or the location where it is, location where it's centered. Let's let this be 0. So there's the center of where it's located, and the spread is really just how far is this distribution spread out, like along the mean or any other value. I'm going to draw a normal curve that actually has higher or greater spread. So I would say this guy has a larger standard deviation than the first guy. So these are three things that help me visualize what a distribution would look like. And we can compute these values both for a sample and a population. So I think we need to be careful here. A random sample should mimic the population. So if you truly drew a random sample, they should look, I'm not going to say exactly the same, especially as n gets larger, the sample should be a better estimate of the population. So back to the last section, the probability density function, this is the f of x that we've been working with. If we graph it, that's a way to visualize what the population looks like. And if we just have sample data values, if we were just given like x1, x2, all the way up to xn, the best way to look at that distribution would be to draw a graph. And often we use a histogram for that. So we can look at the shape of a sample by using graphics, histograms, box plots, otherwise. So let me go ahead and, I figured out how to move this guy up. So how do we calculate these measures of just location, first of all? So I'm going to go down to the sample first, because I think it makes more sense. If these are the values that are your sample data set, then the mean within the sample we always call x bar. So this is the mean for a sample. I think that's the important point with this definition, because there's going to be a definition for the sample and the population. Population, you have everybody. Sample, you just have a sample of the data. So I know you know this one, right? I'm just going to sum up my x's. Sorry, they don't look very good yet. And I'm going to divide by n. And to write this more compactly, often you'll just see the sum of xi from I equal 1 to n divided by n. So if you believe that, which I'm sure you do, that's just the mean of a sample. It's kind of where it's the balancing point. The mean is a measure describing, where the data is balanced, right? If you put a fulcrum there, where's that point that's the nice balance between the left and right side of that distribution? So if you go with me there, then the mean of a distribution or of the population we usually call expected value of x. I'll use that interchangeably with the Greek letter mu. Mu you probably have heard of as the mean of a population. So notice we use different notation for the mean of a sample and the mean of the population. And this should reflect the idea that I'm right? Summing a bunch of values and dividing by their probability. So like over here, I'm really just taking the value x1 and dividing by n, the value x2 divided by n, the value xn. But this is assuming all the data values in my sample are equally likely. But in a population, you might have more weight on one value than another. So for a discrete random variable, what I'm doing is I'm multiplying the x value by its weight, which is f of x. And this is for discrete, so be careful. Remember, discrete was defined for just discrete x values like 1, 2, 3, 4, 5, and so all I'm doing is multiplying the probability by x to get a representation of how likely those x values are. But, and I shouldn't draw, it's not equal to, so be careful. I'm trying to go over to the continuous world. When we go from a discrete to a continuous, we go from summing to integrating, and so I want to follow the same definition and just say f of x times x dx over the support. So I haven't written in the support, but that's the idea. So this is how I would find the mean of a distribution for a continuous random variable. For discrete, I should write here continuous in case you look at this later and say, what was she saying? Okay, I have 4 dogs, and almost every video you'll probably hear somebody barking. The sample mean is really a good estimate of the population mean, and I would say, as you know, that estimate's getting better and better as n goes to infinity. So it's a good estimate, but of course you'd rather have the population if you want to know the truth, but often we don't. We're going to have to use a sample. So let me go back to pulling this up. So here's an example of finding the mean of a population. So we're given that a distribution has this shape, and I'd like to see where this guy is centered, how much spread he has, what his shape looks like. And I can see from the E right here, right, I'm going to have an exponential shape to this data. So I already put this in mini text. I didn't want to have to worry about doing this. Let's go over here. I didn't want to have to worry about doing this while the video was going. So I'm going to define that's the distribution. And first, I just want to look at a plot of it. Let's go from t equals 0 to 100 just to get a basic idea. Wow, okay, we didn't need to go that far, I should have thought. Let's just go to 20. Okay, it's getting better. And actually, I was wrong, right? This doesn't have an exponential shape. I should have saw that t was raised to this power. It has more of a normal type of shape. I mean, not exactly, but it has, yeah, kind of a bell shape to it. The center has to be somewhere around, right? The center looks very close to 3 or 3 point something. Pretty tight spread. So the way I would find, well, first of all, remember the other day, if I wanted to find the probability that the random variable t is greater than 3.5, we would just integrate f of t from t equals 3.5 to infinity, and that gives me the probability, right, that this guy is past 3.5. I probably should have even checked, right? If I integrate f of t from t equals 0 to infinity, what should you get? I mean, this guy is supposed to be a legal density function. It better integrate to 1, pretty close. And now I want to find the mean. I'll just call it mu. That's the integral of f of t times t over the support. And this is how we find the mean. So our mean is about 3, and that's what we said. It looks like it's centered, like the balancing point is somewhere very close to 3, and there's the value. So let me see what else we have here. Oh, we also have to talk about percentiles. So if x is a random variable, then the kth percentile in the population is given by the following value q. So I'm defining the percentile of a population. So let's just put pop there for let's write population. So it's that value that leaves q percent to its left. It's less than or equal to, so kth percentile. So let's just put the value q here, and how much data is to the left of q. Let's say this is 95%. So Q, we would say, is the 95th percentile of this distribution because it leaves 95% of the curve to the left. So since we know the function that leaves or calculates area up to a point from its left is capital F, we can just say it's the value Q such that when I divide K over 100 and I put Q into my cumulative distribution function, that I get this value. So I think I just made it sound really, really hard, but it's not. So the kth percentile is the value of Q such that K percent of the population is less than or equal to that value. And there's really not a nice formula for this for a sample. I mean, there's not just one single, hey, I can give you a formula to wrap it up, but there is for continuous random variables. So let me see, the 50th percentile, meaning half and half, there's 50% to the left and 50 to the right, is the median. The location now is simply, I'd say, the center in terms of it's cutting half your data values are to the left and half are to the right. I'm not talking about area now. I'm just talking about if I lined up all my data, half left, half right. 25th and 75th are known as quartiles. And so that's what you're finding there. And let me see if this goes. I don't remember if this kept going. Oh, yeah, for reliability, I want to find the 95th percentile. So by picture, here's what's happening. We drew that picture already, right? So I'm just trying to draw the best I can of what we got over there. This was centered at 3. So the 95th percentile, I'm going to say, is this value right here. We'll call it Q. That leaves 95% of data to its left. That's the 95th percentile. So I can use f of q. So if I find capital F, I can find it. Or for me, sometimes I think it's just as easy if you say from 0 to q and you integrate f of t dt, what is that value q that gives you 95% of your data, and then I would just solve this guy. So I'll just set it up for now, but that's what I'm doing. If I wanted to find, let's say, let's say that maybe this was 10%. So if I wanted to find the 10th percentile, I would just set this thing equal to 0.1. So I'm really just finding that value that cuts off that proportion of data to the left. Unless that it looks like the last thing he has on here is the box plot. So this, I guess it is harder to make. Wow, I thought I would be very fast, but I don't think so. So in Minitab, sometimes a way to look at percentiles and quartiles is through a box plot. So I went ahead and put his data in from this section, and a box plot is a graph. It's underneath the graph in Minitab. It's called box plot, and I just go ahead and I want a simple box plot, and I want to graph weeks and look at the spread. So here's the box plot. It's a box that the bottom right here is Q1, the top is Q3, so 25% of data less than him. Let me go ahead and click. Oh, well, it should show us when we click on this guy. Come on. Yeah, there we go. So it shows us quartile 1, quartile 3, the median. IQR is the spread between quartile 1 and 3. So anyway, what you want to know right now is you can see your there's your median. So half of my data values are to the left and half are to the right. It's not the balancing point. And you can kind of see the spread. We have some outliers up here. I think I want to go ahead and add to it the mean. Well, let me do that. I forget at the moment how to add the mean to it. Add x-axis, data labels, title, data display. Yeah, so, this lets me do it really nicely. So let's go ahead and put the mean in here. And you can see there's the mean and there's the median. And that's not surprising, right? I have these really high, unusual values, outliers, that if you average, right, the balancing point would be more toward the right tail. And I'm going to say this distribution is positively skewed because, right, anytime it's pulling out toward the right, it's going to pull the mean, which is the average, toward the right. So in this case, it's just, do you want to use the median or do you want to use the mean? And some would say the median is probably a better location of center, just because it's not being biased by these outliers, where the mean is definitely being affected. And for the median, it doesn't matter. You're just counting so many data values in and counting so many data values in. So I could wipe off a couple of these from both edges, 2 and 2, and I'd still have the same median. So this will go on throughout the course, but typically when your distribution's skewed, if it's skewed right, it's going to pull mean right, left skewed, mean left, and then the center gets a little bit confusing. But if you do report both the median and the mean, people would understand that your data then is skewed if they're not the same. I wish it would come up again with the, come on, Minitab. Oh well, I just wanted you to see again the mean, the median, what the values were, but it's not playing very nicely. So let's go over, and I think, great, a sales representative. I think just to keep shorter, I think I'm just going to end it here. Let me see. A sales representative has collected failure data of 80 pressure sensing devices from his company customers over 3.5 years. These devices fail for a variety of reasons. The sensor using the available data, the longest lasting 25% of devices last longer than how many weeks? The longest lasting 25%. So this would be, if I go back to that picture I just drew you, this value is just Q3. He's asking you for, right, in your box plot, here's your box plot, here's quartile 3, well, there were whiskers on this guy, but here's Q3, and it's the value such that 75% is below it and 25% is above it. So Q3 would be that cutoff value for the 25 longest lasting of those sensors. Would I summarize this with a mean or a median? I would get both, and then just by knowing that the mean is right here bigger than the median, I would know I have a positively skewed distribution. So that was even way long, so I have to even figure out how to make them shorter, but for now, that gets us through at least the location spread center of data. So I'll stop.